Hello, everyone. Thanks for coming. I'm Krishna. I work at Pinterest. I'm going to talk to you today about how we are using Hadoop to build Pinterest, which is basically what we think as a data product. To start with, I don't know how many of you are familiar with Pinterest. Pinterest is a visual bookmarking tool. It allows you to discover creative ideas that you can actually save to a board and actually go do it. An example could be like a recipe that you want to cook at home, or a travel destination that you want to go for a holiday, or a book that you want to read, or a movie that you want to watch later. So it's a very personalized discovery engine that we are building. A little bit about me. I'm Krishna. I work on data engineering at Pinterest. Before that, I was at Twitter and Bing, working on search and data platforms. So this is a collection of my pins. So if you're interested to follow any of my boards, you can follow me on Pinterest at Krishna Gade. Coming back to what Pinterest is. As I told you, Pinterest is a data product. What does that mean? It means that we use data for pretty much everything. So the feed that you go to Pinterest when you actually log into the site is what we call a smart feed. It is a feed that we construct based on what interests that you have followed in the past, what pins that you have pinned, what things that you have seen on Pinterest. So it's basically generated sort of half offline, half online. A large portion of the data pipeline runs on Hadoop. Our search index creation happens on Hadoop. So does our promoted pins, which are basically advertisements on Pinterest. And then we use Hadoop for our A/B experimentation pipelines, computing our business metrics, our spam control, and a lot of stuff. So to start with, this is the main agenda that I'm going to cover in this talk. Why do we care about data at Pinterest? How is Hadoop helping us to leverage the power of the data? And then what are some of the tools that we've built on top of the Hadoop platform? To start with, why do we care about data? Right? Just going back to first principles. This is a fun trivia. This is one of the co-founders of Pinterest. Is a very tall person. And let's say you're asked to guess his height just looking at his picture, right? It's probably you don't have much data just except for the picture. So let's say I give you a little bit more context. I tell you that he's carrying a credit card, which is like 3 to 4 inches in height, and that gives a little bit more context to guess his height. Let's say I put Evan next to Ben, the other co-founder, and tell Ben's height is 5 feet 10 inches. It now gives you a little bit more context to guess the correct height of Evan. So if I put Evan in the middle of all Pinterest employees and give you all the heights of Pinterest employees, it might give you more context to be more accurate with your guesses. You probably know where I'm going. So I can actually tell you, if I just put Evan next to a 6'5" giraffe, then you can actually very accurately guess the height of Evan. The whole point of this exercise is, the more context that I present to you, it reduces the uncertainty in your guesses, which improves the odds of you making the right decision. And this is what we believe at Pinterest. And pretty much everything that we do at Pinterest, coming up with validating new ideas, or experimenting with new features, improving existing features, or throwing away features that are not working, are all data-driven. So, and how is Hadoop helping us do this, right? And to start with, let's look at some of the numbers, the scale at Pinterest right now. We are currently indexing about 50 billion pins in our database. These are pins curated by tens of millions of users, saved to close to 1 billion boards. In total, if you include all the pins and all the metadata associated with pins, we are carrying about 40 petabytes of data. All of Pinterest infrastructure is on Amazon, so all of this data is on Amazon S3. We are processing about 3 petabytes a day. We have many Hadoop clusters and thousands of nodes worth, and we have about 200 engineers working at Pinterest. So before I tell you like how Hadoop is actually being used, I want to give you like a quick overview of how the data architecture at Pinterest is. To start with, we have app servers that are logging all the user interactions to a local logging agent called Singer. It's basically our own implementation of something like Scribe or Apache Flume, which then sends all of these log events to a centralized queuing system, Kafka. And from there on, the log data goes into S3 through this component called Ccore. We had to build this thing to pull the logs from Kafka to S3 and overcome some of the eventual consistency issues of S3. It's also an open source project that's being used at Airbnb and Uber right now. So, and from there on, like once the data goes into S3, it is then loaded into our many Hadoop clusters. Hadoop itself, we use Qbol, which is a Hadoop service provider for us on top of Amazon to run our data pipelines. And we have some custom infrastructure, which I'm going to talk to you about today, Pinball, which allows us to schedule all these workflows and to process this data. And eventually, the processed data, some of the processed data goes into the product, like to power features like the home feed or search or promoted pins. Some of the analytics data goes into our analytics system called Pinalytics. And then aggregated data goes into Redshift for ad hoc analysis by our data scientists. So when we started actually working on this thing, we wanted to build like a self-service Hadoop platform to meet our needs. And these are some of the requirements that we thought like would be good to meet. So one of the things is like, because we are not an on-prem installation, we are on the cloud, we wanted to take advantage of the elasticity component of cloud. We wanted to be able to spin as many clusters as possible and shrink and grow each cluster as and when we want to, take advantage of the spot instances of Amazon to create temporary clusters that do like a specific backfill job or run an experiment. So a lot of things like elasticity, supporting multiple clusters, ephemeral clusters was very important. We also wanted to have like a shared data store so that clusters can share data easily between them. We wanted to make the deployment of data jobs way, way simpler. And we wanted to provide some sort of isolation for our developers to be able to run their jobs and not interfere with each other. And then we wanted to provide some sort of easy access control so that we can actually add and modify access of developers. So in order to meet these requirements, we came up with the following design choices. The number one design choice that we started with, which is sort of different from what people do on-prem, is decoupling compute and storage. Traditionally, if you see MapReduce takes advantage of data locality by keeping the data in HDFS, and which makes the processing faster. But we found out in practice that the network I/O is not that bad compared to the disk I/O, especially on S3. So we said if we could pay a little bit of marginal overhead to network I/O and then separate the storage from compute, we could meet a lot of these requirements that we started out with very easily. So we started out having all of the data on S3 as a ground truth. And all the Hadoop clusters are basically stateless. So we can spin up as many Hadoop clusters as possible. And the Hadoop cluster would read the data. The data jobs will read the data from S3. And they temporarily are cached in HDFS, which as you see in the picture, the transient HDFS. So this allows us to not only spin up many Hadoop clusters, to spin up temporary Hadoop clusters on spot instances, which are not guaranteed to be there all the time. So this was a huge advantage in the end. The second design choice that we made was to use Hive and then use Hive metastores as a centralized truth for metadata. So we picked Hive because the SQL interface was very simple and very well understood across industry by both engineers and non-engineers. So a large portion of the data jobs that we write at Pinterest are Hive jobs. And so not only that, we found that the Hive Metastore allows us to actually keep track of all the metadata, not just by the Hive jobs, but we also all the rest of like cascading or pick jobs that developers write. So it gives us like while the true the real data is on S3 or the local HDFS of a Hadoop cluster, the Hive MySQL stores the centralized metadata. And one of the other advantages is listing files in S3 is very slow. So being on Hive, people can actually go and use like describe table, those kind of like semantically beautiful SQL statements to figure out like what's going on, how are the various Hive partitions looking like. So the third design choice was we wanted to make the deployment very easy. When we started on this project, it took us like close to 45 to 50 minutes to like schedule a job on a Hadoop cluster, because we had to deploy like the image, the core Hadoop libraries, and some of the NLP libraries that our developers wanted to use, and then configure them, and then deploy the user code. So we split up our deployment into 3 layers, so that the bottommost layer, the core stuff, the Hadoop jars, the NLP jars that almost change very infrequently, are baked into the image. We call it the baked AMI, and then are pre-installed on the cluster. And then any sort of customization through configuration happens through Puppet. So initially, we ran Puppet instances on all the Hadoop instances, and all these Puppet instances would then talk to a Puppet master to pull the configs. But we quickly found out as we spin up clusters with many hundreds of instances, this was not scaling. So we went with a masterless Puppet, where all the Puppet instances would pull the configs from Amazon S3, and then there is a consistency checker service that goes across all the Puppet instances to make sure that all the config files are consistent within a cluster. And then on the topmost layer is where most of the time the developers are sort of dealing with. This is where we basically, as a developer, we created a special directory on S3 where you can basically put your user code and user level configs, which then get sort of replicated onto the similar directory on whatever Hadoop clusters that you are deploying to. So this basically dropped our deployment time for a job from 45 minutes to like 5 minutes. And then the fourth design choice that we made was basically building this executor abstraction layer. When we started building this platform, we were using EMR, Elastic MapReduce from Amazon, for Hadoop. EMR actually works well with S3. It plays well with Spot instances. And it was reasonably stable. But as we started scaling up our Hadoop clusters, it was not very reliable. And it also had its own proprietary version of Hive, which was sort of like made our application code get some of the EMR functionality. So as time progressed, we started seeing a lot more EMR functionality started creeping into our application code. This meant that if we were to switch to a Hadoop service provider, it wouldn't be very easy. So what we did was we created an abstraction layer that kept the service provider's functionality, which we call the executor. So we wrote an AMR executor that encapsulated this functionality, and then which insulated our application code away from whatever Hadoop service provider that we were using. So this allowed us to migrate or to test first Qbol, which is a Hadoop as a service provider on Amazon, and then migrate slowly without causing disruption to our users. So right now, we are 100% on Qbol for about a year. And this also allows us in the future, if we want to use our own managed Hadoop inside Pinterest. So, and this is like a slide on why we chose Qbol. So a few things that Qbol did very well was they were actually using the open source Hive, and they were actually the ex-Hive team of Facebook, so they actually made it like much better. They had very tight integration. They had a really, really clean GUI for our non-engineers to use without knowing very much about Hadoop. They had like very good Spot instance support. For example, we could set up a cluster with on-demand and Spot mixed, and they would cleverly sort of use instances as and when they're available and make like the cluster cost efficient. They also supported this baked AMI customization that we wanted. Currently, they're also providing Spark as a managed service for us, which we are testing for our machine learning use case. So this is like how things are right now in terms of like the number of workflows. We're running a few thousand workflows, a few hundreds of workflows, and a few thousands of jobs. A particular workflow, like our search indexing workflow, consists about 500, which is like the largest workflow, has about 500 plus jobs. We're processing about 3 petabytes of data, and we support like Hadoop streaming, cascading, Hive, and Spark jobs. So I'm gonna now talk about a system that we have built that allows us to sort of manage all these workflows, schedule them, and build all the data pipelines that I talked about. So Pinball is a workflow management system that we've built. We've open sourced this recently. Pinball's equivalent in the open source worlds are things like Apache UZ or Azkaban or Luigi. When we started writing Pinball, I don't think Luigi was open sourced. The reason why we started writing Pinball was we were actually using Azkaban before, and it was not like we felt it was very inflexible. I mean, it was like a big monolith, and we wanted something that was easy to debug and something much more flexible, so that we could actually run many different kinds of jobs and then integrate them into the same workflow. So some of the requirements that we came up with for this system were it should be based on simpler abstractions, so that anyone would be able to understand it easily. Extensibility was a big thing. We wanted to keep as much computing as possible in like stateless components. And so we wanted to keep like the state management minimal and centralized. And this allowed us also to scale horizontally to add nodes because most of the components were stateless. And wanted to be upgraded without aborting workflows, and also add rich features like auto retries and things like that. So this is the design of Pinball. Pinball has a master's service that keeps track of the internal state. It keeps all the state in a database. We use MySQL for it. And then there are a bunch of workers that are actually executing these tasks. There's a scheduler component that figures out when to run a particular workflow based on the policy specified. And then there is a event generation module that, which basically is using, like every time a job completes or fails, it generates events for the downstream jobs, for whether to make them runnable or keep them waiting. And then we have a UI that allows the developers to actually see the state of the current workflows and how they're doing. So start with like a workflow. This is like a typical workflow. You can see like all the green. This is like a screenshot from the UI. All the green ones are the jobs that have completed. The red ones are the ones that have failed. The blue ones that are running, and the gray ones are the ones that are still waiting to be scheduled. And as you can see, the edge is like a dependency, which is run after dependence, and each node is a job in this graph. So the job state is captured in a token, which is kept in the database. A token has a job name. So we used a hierarchical naming convention to name the job. So a workflow instance, and the job name. And an owner, which worker actually is running this job. And an expiration, when should this job token be expired. And some data associated with like the job definition and things like that. So this is the state machine. A job can be any one of these three states. Either it's waiting to be runnable, so it's waiting for all of its inputs to be available, and once all of its input is available, then the worker puts it in the runnable state, and then actually runs it. And if it succeeds or fails, it again puts back into the waiting state. So this is how the master and the worker interact. So compared to like the Uzi interface, this is a polling-based system, so there is no async communication happening here. But the beauty of it is like the state management is centralized, so it's very easy to scale the system. So because there's only one master that's dealing with the state management, we can spin up as many workers as possible to scale for the throughput of job submissions. So workers claim and execute these tasks as shown in this diagram, and as I said, like it's horizontally scalable. So some more about master. All of the state is kept in memory, and each state update is basically persisted first to the database before the master replies to the client. And then master, we've made a conscious decision to run the master on a single thread so that we don't sort of run into concurrency issues of mutating the state by like many threads at the same time. So this is like a sort of pseudocode for how a worker would run. So you can think about it as like this is how it's polling. It basically tries to get like the next runnable job from the master. If the job is there, it schedules it and marks it as running. If the job has failed, then it first looks at the workflow policy, and depending on it, it either aborts the workflow or does nothing. Otherwise, it then informs all the downstream jobs that, hey, the job is succeeded, and then picks up the next downstream jobs, and then sees if their inputs are available, and then marks them runnable or keep them waiting. So that's very simple. This is how it works. So this is open. We've open sourced this like about 3-4 weeks ago. It's available on GitHub, Pinterest, Pinball. Feel free to use it. There's a Pinball users mailing list. You can give us feedback on how you sort of like see it. So going back to like how we're using how Hadoop is helping Pinterest. I'm going to demonstrate a couple of data-driven products that we have built using Hadoop. The first one is guided search. This is basically query suggestions beautifully designed. So for a given query like Brussels, we show these guides called, like in this case, Sprouts, Belgium, things to do, chocolate. So these guided these query suggestions are computed by when we look at like the session logs of our users and looking at frequently co-occurring queries within sessions across user sessions, and then also looking at like the descriptions of the pins that where the keywords have occurred together, and all of this data gets aggregated together, and then like we run sort of like picking up like the top K so extensions for a given keyword. And another example is like related pins. This is like where you see a pin in Pinterest. We show you like a rail of related pins. Again, this is like we collect, aggregate all the pin level features. We also look at the image features, like what color is the pin is in, what are the objects inside the pin, and then we run like machine learning models to figure out like the relatedness of any two pins. So this the third part of the talk is going to be around like some of the tools that we have built on top of the Hadoop platform. There's one tool that I'm going to talk about, which is Pinalytics. Pinalytics is our data analytics engine, which I've shown you in the data architecture diagram before. What Pinalytics, we use Pinalytics every day to look at how Pinterest is doing, how various features on Pinterest are doing. So the way that we built Pinalytics is, as I showed you, the data goes from Kafka to S3, and from there, the data processing pipeline picks up, and which then feeds into the Pinalytics reporter. So Pinalytics reporter is this library which we give to our data analyst or any engineer in the company who wants to create their own reports for their particular features. I'll show you how they can actually easily, with Hive, they can create like a Pinalytics report, which then gets persisted into a thrift service, which writes this the report data into HBase, and there's a web app that which acts as a front end to display the time series data. To start with, the user interface, we use Highcharts for showing the time series graphs. The dashboards are customizable. We also support like many built-in dashboards and also many other user-defined dashboards. In addition to this user interface, Pinalytics also has anomalous metrics tracking system, which monitors all the metrics every day and computes any inconsistencies and sends emails to subscribers of those dashboards saying like, hey, the metrics are not correct today, things like that. We also created like reporting, like formatted dashboards, which allow data analysts to actually combine a set of dashboards and add annotations and summaries and present to senior management. We added things like metric manipulation, so we could have like two sort of line graphs, and you could do simple arithmetic to either like do like A divided by B or like A, or sort of like A percentage B, so like many sort of composite metrics that you can generate from a given set of metrics. So the data model for Pinalytics is we use HBase for our for storing this data. So there's a key. The key is a composite of like the date of the metric and many segments. And then when we actually try to present to the user, we do a scan and then aggregate the rows. So in this case, for example, if we are showing the date and the country and gender as a segments, so for let's say if you're asked to, let's say this is like monthly active users, we then aggregate all the if someone asks for like UK users, we just aggregate the two rows and then sum them up. So this is the architecture diagram. So as I told you, HBase is the backend for the system, which stores all of this reporting data, and the thrift service uses HBase to do this scan and aggregate operation. And the aggregate operation and scan and operation are delegated to HBase region servers, which use the coprocessors to do this local aggregations and send the final aggregates back, and the Pinalytics thrift service sends back the actual metrics for rendering. So we chose HBase because we didn't want to do any application level sharding. For example, if you wanted to use MySQL, you had to do the sharding on application level. We didn't want to do that. It also had flexibility in aggregation, so we could use like fuzzy row filters to get sort of like rows that match a particular filter, and coprocessors that I talked to you about. So HBase stores two kinds of tables, basically, the reporting data and the metadata associated with the reports. So the fuzzy row filter, just a small example. So let's say the composite row key is a metric, time, and a bunch of segments. So you can specify, let's say you wanted to see like monthly active users for January 1st, and you didn't know like what the other segments were, like let's say that was the country code and something else. So you could create a fuzzy row filter that would say like match the ones that you want them to match and don't match the ones that you don't know about matching. So you could basically get the starting and ending row for that filtered by the fuzzy row filter. So again, HBase Coprocessor. So we use region servers for local aggregation, and then the final aggregation happens on the thrift service. Obviously allows us to reduce the network I/O because we are sending a lot less data back up, and we found it to be very fast. So Reporter is this client library that I talked to you about, which allows developers and data analysts to create reports. It allows people to sort of do arbitrary metrics and segments. This is like a small example. Let's say someone is creating a weekly active user report. They would extend like a class, a Pinalytics wide report, and specify the metrics that they want, like the weekly active users or weekly active repinners or monthly active users and the segments that they want to, and then specify the actual query, the Hive query that they want to run. And the output would be like something like this blob where a date and the segments and the actual values for those segments. So we use this reporter to pre-compute a lot of core metrics, all the activity of our users, event counts, retention, signups. All of them are spam filtered. They're segmented by like gender, country, the mobile platform that they use. So we have deployed the system around October last year. Since then, we've had like a terrific uptake. About 400 unique users. We monitor the system using Google Analytics internally, and we see about 800 page views a day, and about 400 unique users, and so far about 1,500 to 2,000 reports have been generated. So with that, I want to conclude. If you have any questions, I'm happy to answer now.
So how do you get around the locality issue if you're separating out the compute and storage?
Yeah, so because we use... So the question was, how do you get around the locality issue if you separate compute and storage? So the source of truth, the truth data is on S3. And when a job is launched on a new Hadoop cluster, it reads from S3, and it's cached locally in the transient HDFS within that local cluster. And whenever it writes the outputs are written back to S3. So S3 is always consistent. So you can have if a particular cluster needs to share data written by the jobs in another cluster, it can actually do that. We do run into eventual consistencies with S3, but they are not very frequent. Yeah, obviously. So because it's a Hadoop cluster that you can see. It has HDFS running on that cluster. It's just acting as a cache and not as a set, as a truth set.
Could you comment on how Pinball compares with Falcon?
Falcon?
So if you don't know Falcon, you probably won't be able to answer the question.
Yeah, so we used Azkaban before using Pinball. We were aware of Uzi. We got to know about Luigi recently. Yeah.
Hi, you mentioned inconsistencies on S3.
Yeah.
This was US East, or was it anywhere?
This is with this is with US East, and so we are. I mean, they're not very frequent, but when they do happen, they cause disruption in our workflows. We're taking we're taking a two-pronged approach to this problem. We're thinking about either having a separate HDFS cluster that could sort of potentially replace S3. That might be a little harder to achieve within the constraints that we have. The other option that we are taking is to actually create an intermediary service that sits between a data job and S3, and actually can consistently report the file listing for anyone asking for it. So basically, it can keep track of all the writes to S3 in a separate database, so that anyone can call it instead of calling S3 to basically list the files, and it always gives you a consistent answer. So this is something that we are working on.
Okay.
Right now.
Have you played with the Netflix Semper?
Yeah. So this is very similar to Semper's idea.
Okay. You didn't, but you're not actually using it.
When we are thinking about it.
Okay. Thanks.
Cool. Any other questions? Okay. Thank you. So I'll be here if you have any more questions.